Hello and good morning. This is our first lecture, first introduction lecture. So we have already done an introduction to the course description. So this is the first lecture that we're having dealing on the content. So once again, this is SPL 2214, which is Natural Optical Phenomena. And this is lecture 1, which should cover content for week 1 and part of week 2. So I'll be doing a second lecture that will cover week 2 entirely and probably part of week 3 according to the schedule that I shared with you earlier. So on this introduction, it is important that we understand what light is and the representation of light. We all know that light can be represented in many ways. Light can be considered as a wave, and light can also be considered as a particle, but the representation, light can also be represented in terms of optical rays. So the field of optics in which you represent light in terms of rays is referred to as geometrical optics. And that is where some of the optical phenomena that we want to look at in this lecture will be considering light in terms of rays. Now, you would want to perhaps imagine that when you are on a sunny beach and you have an umbrella, you probably do not consider uh, light at that point in terms of wavelength, frequency, and so on. All that you want to do is to put the umbrella up there so that it prevents rays from reaching your body. So in that aspect, the reason why you consider umbrella is because the umbrella could be maybe say 1 meter in diameter, and we are considering light that has a very, very small wavelength. If you consider light, that the visible light having wavelength of between maybe 400 nanometers and maybe 800 nanometers, then an object like an umbrella will very much block a lot of rays that is reaching you. But when you have an object that is too small or maybe comparable to the wavelength of light, then that will not prevent rays from reaching your body, but instead it will create other optical phenomena like diffraction, and so it will just spread the same way you have sound waves spread around obstacles, and that is an effect that is known as diffraction. So the importance of this slide here is just to compare, like when you talk about light, you talk about light in terms of wavelength that is in the range of nanometers. And so when you block the rays of light with an object that is much, much bigger, then of course you know that you are going to block or you're going to prevent the transmission of light reaching the end. But when you use an object that is comparable in size, in terms of wavelength and the object, then you will not get the effect that you so desire. And that's why I've brought here an issue of umbrella in comparable to the wavelength of light. So in geometrical optics, light does not bend around corners. Okay, that is what we refer to as the rectilinear propagation of light. We of course take light as if it is traveling in straight lines if there are no obstacles. But if you want light to bend, of course you must reflect it so that it takes a different trajectory. Otherwise, in geometrical optics, we consider light as traveling in straight lines, and I don't think that is something that is very new. So that's it. So very closely to that, there's an element of shadow, which is one of a very simple natural optical phenomena. We know that shadows are brought about by an object appearing in the path of light. And so the prevention of light from reaching another point produces a dark region, right? And probably that is what we know as what we call shadows. So to cast a shadow, you need light from a fairly concentrated source, like a fluorescent bulb, could be a sun. So if you want to have a very sharp shadow, then it must come from one point. And light that comes from a single point is, of course, referred to as a point source. So even sun can be considered as a point source if the distance is too much. I mean it is far away. If the distance is too big, then the source of light looks like a point. So in that case, the distance makes sun be considered as a point source. And we can also have a point source like a bulb. Okay, you only need to arrange your setup so that you create enough distance, or if the distance is not too big, you can create something like a small hole so that light appears to be coming from such a hole. So that will give you, or that will produce, a very sharp shadow, right? Then of course you need like a platform where you will be able to see the shadow, and that is what we call now the screen, which in most cases, if it is flat, then you are able to see uh, um, a likeness, a close likeness of the object and that shadow. So the screen redirects incident light into all directions so that you can see the shadow that maybe you want to see if you're doing it as an experiment. And then, of course, the part that you see the light falling on the screen, it simply means that is the light that is now reaching your eye. The dark portion is where light does not reach your eye. Okay, that's why it is dark, because it does not, the reflection does not get to your eye. Yeah, so that's it. And then, of course, the light rays that are blocked don't reach the screen. So the places where they would have hit they would have hit the screen are of course dark. And now that is what we call now the shadow. So that one is something that is simple, that all of us should be able to explain, that a shadow is brought about by light rays that are blocked from reaching the screen. So that those parts, the portions of light where there's an obstacle will appear dark, and the portions where does not is not blocked will appear with light on the screen. So your eye will be able to detect the region of darkness and the region that has light, and then you can see the image of the shadow. So in terms of drawing rays and locating the shadow, we normally use rays. In geometrical optics, we use rays, which are straight lines from point source to the edge of the obstacle and continuing them to the screen. So I think we can picture that how it is done. You have one ray that goes past the edge towards the screen, then the other one of course goes to the other edge, and then of course the middle part will appear dark. But again, as we shall see later, all shadows are not the same. At some shadows will appear to be darker in some areas and gray in others. So again, in terms of representation with geometrical with rays, we can actually be able to see which parts are dark, which parts are gray, using rays, which are just straight lines. So these rays or these lines separate regions where rays reach the screen, from the region where they are blocked. Okay, I think the next slide should be having a figure. The resulting shadow resembles the obstacle, but it is of course only a flat two-dimensional representation. So again, yourself, if you're the object that is supposed to be creating a shadow, yourself, you are three-dimensional, but the screen will only show the two-dimensional part, okay, or the two-dimensional representation of yourself. So a shadow largely is two-dimensional as opposed to the object which is three-dimensional. So again, we also have some shadows which necessarily do not have to appear on a screen, like what we call the silhouettes. Okay, you can see the picture on the left there. So a silhouette is basically um, uh, like an object casting shadow on one side of itself. So that means the source of light must be on the opposite side to where the observation is being made. So whatever kind of representation or the portrait that is observed is referred to as a silhouette. So this now brings an aspect that an object can cast shadow on itself, right? Aside from an object casting shadow on a screen, you can also have an object casting shadow on itself. The same way we have the earth, right? We have the earth, so we have one side is day, the other side is night. So the side that is night simply means that the object is casting a shadow on itself. Okay. Yeah. So yeah, that's the other aspect. Then we also have aspects like the X-rays. Okay. So an X-ray, in essence, is just a shadow of the object or the part that is exposed to the X-ray. Of course, we have aspects like diffraction that takes place, but of course, that diffraction is brought about by obstacles. Remember, the explanation for diffraction is that it is the spreading of light or bending that is caused by an obstacle. So, with that in mind, when we have an obstacle in the path of the X-ray, then we can have an image representation. Now, on a screen that is made photographic in nature, so that when it is developed, the doctor will be able to see the internal part of the body that is expected to be seen. So if it's a fracture that is being detected, the fracture will simply come out clearly because the part with the fracture will not or will allow more light to pass as opposed to the part that has a bone. So that one is again a shadow, but there's an element of diffraction that takes place that gives out the image. So yeah, we have talked about something like the earth casting shadow on itself. So the earth prevents sun's rays from reaching the other side, which the other side now in this case is the night. So when you watch the sunrise, your back is in such a shadow, so your own shadow. So again, here we are talking about an object casting shadow on itself. And we're also saying that shadows help artists represent objects more realistically. For example, unsupported object in mid-air is portrayed detached from its shadow. So you have an object that is hanging in the air and then light on one side. So it's again looks like the object is portrayed to be detached from the shadow. I believe you can be able to picture that. And then of course you have very long shadows which are created by things like very tall buildings or very long mountains, and that is what we refer to as a twilight. Okay, twilight. So that again is just an aspect of blocking light, uh, and so on. So again, the question again that is interesting here is that what happens if you have more than one source of light? Okay, like in the picture that you can be able to see here. So when you have two sources of light, each source will produce its own shadow. Okay? Each source produces its own shadow, but there will be an area that the two shadows will overlap. So an area that has both shadows overlapping will be darker compared to the rest of the shadow. Okay? So that's what happens when you have two shadows. I mean, sorry, not two shadows, but two sources of light. Each light will produce its own shadow the normal way. But now the area that the two shadows will overlap will be more darker compared to the rest. So this concept is the same concept that is seen when you have a very long tube, like the fluorescent tube. When you have a very long tube, it means that each point on that fluorescent tube behaves like a point source. So that each of those point sources will produce a shadow, and those shadows will be dark where they overlap. All right. So when you have an extended source, you will have the central part becoming more dark compared to the edges. Okay. And of course, we are going to discuss a little bit about the center part, which is more dark, and the area around, which is gray in color. So an extended source will produce two regions of a shadow. The central part will be very dark, and then on the periphery, you will have shadows that will be uh, gray in color. So the concept for a fluorescent tube and or any other extended source just comes from the fact that if you pick two sources of light, then each of those sources of light will produce a shadow, and those shadows will overlap, and so the area where they overlap will appear darker as compared to uh, the other part. So the central part, which is dark, is referred as the umbra, right? Is referred as the umbra, and the regions where the shadows don't overlap will be partially dark. That means they appear grayish. They will receive light from some parts of the extended source, um, but not other parts. So that area which is partially dark is what we call the penumbra. Again, these are not terms that are new, but again, you should be able to explain them. If you're asked to explain the difference between those two, you should give like an extended explanation of how a number comes about and the penumbra. So you can figure out the darkness of a shadow by supposing you are at the point on the screen and looking back towards the source. So where you are, it will be darker in proportion to the amount of extended source that is blocked from your view. So if you look at this figure here, if somebody stands on the portion that is gray, we'll only see a section of the source of light. Okay, you look at that figure, you'll be able to see these two people. Whatever is shown here, I don't know whether you can see the cursor. They are only seeing part of the source of light, which is the sun. But somebody who is located at the center, the dark side, the dark part, sees completely nothing. The person is in the dark, does not see any source of light. So this kind of arrangement brings us to something that is very important, natural optical phenomena, which is known as an eclipse. Yeah. Yeah, so an eclipse is basically the arrangement of the sun, the earth, and the moon Yeah, so the aspect of arrangement of the sun, the earth, and the moon in one straight line is described as an eclipse. So the first eclipse that is usually very interesting optical phenomena is when you have the sun on the extreme end, you have the moon in the middle, and you have the earth on the other end. So what happens, of course, is that the rays from the sun will be blocked by the moon, and they'll not be able to reach the earth. So like we have said, depending on the position of the moon, the umbra sometimes can fall on the earth, so that if you are at the umbra, you will not be able to see the sun at all. But those that are in the penumbra region will just be able to see a portion of the sun. So when you look at this diagram down here, this is what we call a time series photograph that was taken as the eclipse was about to occur. So on the extreme, first of all, you see um, there is a section, the sun is seen and part of the moon is seen trying to block the sun. Then after a short while, the moon, the area that is blocking the sun increases until you see now the moon completely blocked the sun. But of course, because the moon is in motion, it continues to move in the opposite direction. So again, you see now a portion of sun being seen until the moon is completely out of the path uh, of the earth. So this is what we call the solar eclipse. Now, it is not advisable to stare directly at the sun, not necessarily the eclipse. Generally, even during the day, staring at the sun for a long time is prohibited because it brings serious damage to your eye. Okay, so the best way, of course, to observe something like an eclipse, because it's a phenomenon that does not happen on a daily basis. But of course, people are tempted to stare at it because it doesn't happen on a daily basis. But when you do that, you are exposing yourself to direct rays from the sun, which is prohibited even without the eclipse. So there are instances where people have done that and they have been reported to go blind or seriously damaging their eyes. So please do not stare at the sun directly for a long time because it can bring serious damage. So the best way to observe a solar eclipse is using a pinhole. So when you use a pinhole camera, you are able to see the image of that eclipse on a screen rather than looking at that image directly. So here we are seeing there are two photographs of the eye. The one on the left side is a normal eye, and the one on the right hand side is the damaged eye as a result of looking at the sun directly for a long time. So when you do that, of course, the image of the sun will try to appear in the retina of your eye, and of course, when the retina is affected, it means even the position. When you just look at an object, you are not able to see it clearly because the position of retina has been affected by the sun. So it is not a good practice to stare too long at the sun during solar eclipse or during any other time because it can permanently damage the retina, which is of course the screen where all images are focused before, of course, the brain interprets what is in the image. Of course, there's a lunar eclipse, which is now when you have this the moon, the moon on the extreme end and the sun on the other extreme end with the other in the middle. So the lunar eclipse, of course, happens at night, and it happens because the moon reflects part of the rays that is coming from the sun. So you have a point where the moon is directly in line with the moon, the earth and the sun. So you're able to see a completely red moon, completely red moon. Okay, so that's a lunar eclipse which happens at night, which is a very uh, more common than the solar eclipse kind of optical phenomena. So the other aspect that we need to discuss is that on what we call the contrails. Okay, what we call the contrails, which are also some natural optical phenomena. Contrail is a short form for condensation trails. All right. But first of all, if you want to, let us picture this one so that we understand what a contrail is. If you are in a very cold place, okay, let's assume it is very cold, very early in the morning, it is chilly, and you blow some air from your breath, you blow some hot air. Normally, you see some kind of smoke that is forming around your mouth. So that one is a very simple concept for the contrails. Normally, what happens because you are injecting some hot air from your body, and the surrounding environment is very cold. So that hot air that is injected into the atmosphere is quickly being cooled down, right? Is quickly being cooled down. So that cooling process makes that air to be what we call is being condensed. It is being converted into some water vapor. It's being condensed. Now, contrails, the normal contrail that we all know is sometimes you see an aircraft that is situated on some very high altitude above the Earth's surface, is moving, and then you see a trail of some kind of white. Okay, let me call it smoke for the sake of understanding. You see some kind of white smoke following the aeroplane. Normally, it is not the smoke, right? That is what we call a contrail because the exhaust gases coming from the aircraft comes out when it is very, very hot. It is very, very hot. And the surrounding environment in that altitude is usually very cold. Sometimes we're talking about something like negative 40 degrees Celsius. And the engine is injecting something like 90 degrees Celsius. So that temperature difference quickly makes the hot air from the exhaust of the aircraft to be condensed. So it turns into ice very fast. And now the moment it turns into ice, which is normally whitish in color, that is what we see as contrail. So a contrail is simply a condensation trail. Contrails form when hot, humid air from jet exhaust mixes with environmental air of very low pressure and low temperature. So that is the difference. That is the understanding of contrails. So it kind of brings what we call cloud formation because the ice itself is an aspect of cloud. So that trail, next time you see an aeroplane moving and you see a very white trail following the aircraft, remember the process of condensation. You breathe out yourself. If you breathe out in a very cold environment, you see some white smoke. That white smoke, it's simply the hot air being condensed. The only difference between now what you're breathing and what the aircraft is producing up there is that what is coming from your mouth is probably maybe 23 degrees, right? and the surrounding temperature could be maybe 16 degrees. So that difference is not very big. But when you think about the surrounding temperature as negative 40 degrees Celsius and very low pressure, and the aircraft producing exhaust gases at a temperature of say 90 degrees or sometimes even more than 100 degrees Celsius. So that difference condenses the hot air immediately and it turns into ice. And that ice is now what is seen. So let's see what is. So contrails and other clouds directly resulting from human activity, because even the fact that you have an aircraft producing hot air is a human activity, are correct collectively referred to as homogene- homogenitas. Homogenitas, right? Like what you can produce artificial clouds by the same procedure. So that is what we call homogeneitas. So depending on the temperature and the humidity at the altitude, the contrail form, they may be visible for only a few seconds, all right, or minutes, or they may persist for hours and spread to several miles wide. So let me again, I've given you an example of breathing hot air into the atmosphere. So that one does not last for a very long time. It probably disappears within few seconds. Why? Because the temperature difference is not very big. But up there, when you see a contrail that lasts for a very long time, sometimes they last for hours. What does it mean? It means the temperature difference up there or the humidity level up there is so high. There's a lot of moisture up there, and so the contrail lasts for a very long time. So we see it in terms of some white smoke, and that is also a natural optical phenomena because sometimes you see it as white, sometimes it is dark. We are going to look at all that. So again, some contrails may spread. Some contrails may spread wider, and of course that is just due to the movement of air, the wind. If the wind spreads it wider, then of course, even if you see the contrail becoming horizontally wider, then of course you know there's a lot of wind. If you see a contrail maintaining a very straight line, it probably means there is little movement in terms of air up there. If the contrail disappears within seconds, it means the humidity level there is very low. There's not too much moisture. But if there's too much moisture up there, the contrail lasts for a very long time. So actually, this can be able, this should be able to explain the aspect of predicting weather. Like if a contrail lasts for a very long time, just remember, just know that there could be rains coming very soon because there's too much moisture up there, and it is just moisture that develops clouds and of course the rain. But if a contrail disappears almost immediately, it means there is less moisture, and so the chances of having rain soon is low. So we have different types of contrails. Sometimes you see contrail casting shadow on itself. Okay, so a contrail